Hello there, and welcome to Sleepy Science Vault. There is a question that has followed human beings across every civilization, every culture, every era of scientific discovery. Not the question of where we came from, though that one is extraordinary enough, but the question of where all of this is going. Where the stars will go. Where time itself will eventually lead. What, if anything, comes after the last light fades? It is one of the most profound questions ever asked. And what makes it truly remarkable is that we are now, for the first time in history, beginning to have the tools to explore and answer. The current scientific picture, built from decades of observation, from the behavior of distant galaxies, from the faint afterglow of the Big Bang itself, points towards something called the Big Freeze. Or, more formally, heat death. The idea is this: the universe is expanding. Not just expanding, but accelerating. Galaxies are drifting apart from one another, pushed by a mysterious force we call dark energy, and over timescales so vast they are nearly impossible to hold in the mind. This expansion will continue until the cosmos becomes cold, dark, and almost entirely empty. Stars will exhaust their fuel. Galaxies will dissolve. Even the slow decay of matter itself will eventually wind down to silence. It is not a violent end. It is more like a long, gradual fading. The universe does not go out with a bang. It dims. But here is what scientists are careful to say, and what makes this story genuinely honest rather than just dramatic: this is still theoretical. Every scenario we have for the end of the universe is built on extrapolating physics that we understand only partially. Dark energy, which appears to be driving this acceleration, remains one of the deepest mysteries in all of science. We can measure its effects. We can track what it seems to do. But we do not yet know what it fundamentally is. And until we do, the ultimate fate of everything remains an open question. This is not a weakness in the science. It is actually one of the most intellectually beautiful things about it. The universe is not required to fit our current models. It only has to be what it is. Because of this, physicists do not speak of a single predicted end. They speak of a family of possible outcomes, a range of scenarios, each consistent with what we currently observe, each leading somewhere different. The Big Freeze is the leading candidate, yes. But older ideas, like the Big Crunch, where gravity eventually reverses expansion and collapses everything back inward, or cyclic universe models, where the cosmos endlessly destroys and recreates itself, have not been entirely ruled out. New data could revive them. The consensus we hold today is a snapshot, not a final verdict. And the consensus does shift. Each time astronomers refine their measurements of how fast the universe is expanding, each time they gather more precise data on the behavior of dark energy, the projected timeline adjusts. The qualitative picture may stay similar, the universe trending toward coldness and stillness, but the details move. Science is a living process, and our portrait of the end of everything is still being painted. What we also don't fully understand is the deeper structure underlying all of this. Quantum gravity, the unification of quantum mechanics with general relativity, remains one of the great unsolved problems in physics. And without it, there are gaps in our picture that could, in principle, change everything. The vacuum structure of space itself may hold surprises. Physics that we haven't discovered yet may introduce entirely new possibilities for what the end looks like. It is even possible, some researchers suggest, that the true final state of the universe may be unknowable in practice. Not because science will fail, but because the timescales involved are so incomprehensibly vast, and our observational reach is so fundamentally limited, that no civilization, however advanced, could ever gather enough evidence to distinguish between the leading scenarios. The answer may remain forever theoretical. A truth the universe keeps to itself. And yet there is something quietly astonishing in what mathematics does allow us to see. The same equations used to describe the Big Bang, the birth of space and time, can, in principle, be pushed all the way forward to describe the end. The beginning and the ending are connected by a single mathematical framework. The universe may be, in some deep sense, self-contained. A story written entirely within its own logic, from the first fraction of a second to the very last. Some models take this even further, suggesting that the ultimate fate of the cosmos was effectively determined in those first instants after the Big Bang. That the initial conditions, the precise way energy was distributed, the exact values of the fundamental constants, encoded the ending before a single star had formed. If that is true, then the universe has always been carrying its own conclusion inside it, the way a seed carries the shape of a tree. There may even be physical relics from those earliest moments, exotic structures like cosmic strings or topological defects, that continue to quietly influence the behavior of dark energy and spacetime across billions of years, subtly steering the universe toward its final state. The end, written into the very fabric of the beginning. And each time our instruments improve, each time we refine the measurement of how the cosmos is expanding, the projected story of the end shifts a little. Not dramatically. Not enough to change the broad picture. But enough to remind us that this is not a closed book. Every new telescope, every new survey of the sky, every new data set brings us fractionally closer to understanding what the universe is actually going to do. We are a young species on a small planet, looking out at something almost incomprehensibly large and old, asking the oldest question we know how to ask. And somehow, slowly, carefully, we are beginning to hear the universe answer. Everything we experience, every orbit, every tide, every beam of light crossing the night sky, exists within a universe that is, right now, being pulled apart. Not violently, not suddenly, but steadily, relentlessly, in every direction at once. The space between galaxies is growing. The cosmos is expanding, and has been since the very beginning. What took centuries to confirm, and decades more to fully absorb, is that this expansion is not coasting, it is accelerating. Something is pushing. Something is driving the universe apart faster and faster with each passing age. We call it dark energy. And of all the things we do not understand about the universe, dark energy may be the most consequential, because it is not a minor detail. It makes up roughly 68% of everything the universe contains. It is, in a very real sense, the dominant ingredient of reality. And we have almost no idea what it truly is. What we do have is a way of describing its behavior. Cosmologists use a parameter, a number called W, to characterize the nature of dark energy. This single value, deceptively simple, carries enormous weight. If W equals -1, dark energy behaves like a fixed, unchanging property of space itself, what Einstein once called the cosmological constant, and the universe heads gently toward a big freeze, expanding forever into cold, quiet stillness. But if W is less than -1, something stranger happens. Dark energy would grow stronger over time, tearing apart not just the space between galaxies, but eventually galaxies themselves, then solar systems, then planets, then atoms. Every structure in the universe, dismantled piece by piece, down to the most fundamental scales. This is called the Big Rip, and it is exactly as dramatic as it sounds. And if W is slightly greater than -1, gravity holds on a little longer. Structures stay bound. The story slows. The universe ages more gracefully before it fades. The entire long-term fate of everything hinges on this one number. And we do not yet know its precise value. What we do know is that dark energy may not be constant at all. There is a real possibility, supported by ongoing research, that dark energy evolves, that it changes over time rather than staying fixed. If that is true, the implications are enormous. A universe with evolving dark energy does not behave predictably on cosmic timescales. It could accelerate and then decelerate. It could build toward a rip. It could reverse. The late universe story, in that case, becomes something we genuinely cannot project with confidence. The question of which ending we are heading toward also depends on something more fundamental, the total density of matter and energy in the universe. There is a value, a critical density, that acts like a dividing line. If the universe's average density is above it, gravity wins in the long run, and expansion eventually reverses. If it is below, expansion continues forever. Current measurements suggest the universe sits just below that critical threshold, in a geometry that is essentially flat, meaning it will likely expand without end. But those measurements carry their own complications. There is a problem in modern cosmology that has been growing more difficult to dismiss, and it is called the Hubble tension. Different methods of measuring how fast the universe is expanding keep producing slightly different answers. Observations of the early universe, using the cosmic microwave background, give one value. Observations of the late universe, using distant stars and supernovae, give another. The gap between them is small, but it is persistent, and it refuses to go away as instruments improve. This matters because our models of the universe's future are only as reliable as our measurements of its present. If those measurements are subtly wrong, if our best fit model is missing something, then everything we project forward into deep time is built on a slightly crooked foundation. The Hubble tension is not just a technical puzzle. It is a signal that something in our picture of the cosmos may need to change. And there are more recent hints that push the story further. Some analyses from 2025 have raised the intriguing possibility that the universe's expansion may already be showing signs of slowing down. Not dramatically, not conclusively, but measurably. If that turns out to be real, it would shift the odds significantly, away from eternal expansion, and toward a universe that eventually reaches a maximum size and then, perhaps, begins to fall back inward. A big crunch, not a big freeze. The idea of a big crunch carries its own strange poetry. Everything that was flung outward from the beginning, slowly arcing back. Every galaxy, every star, every particle drawn inward by the one force patient enough to outlast everything else. And if some models are correct, the timeline for this could be startlingly close in cosmic terms. Certain recent calculations suggest the universe might reach its maximum extent roughly 11 billion years from now, which would mean, if a collapse follows, that we are already living near the midpoint of the universe's total lifespan. That we are not early in the story, but somewhere in the middle of it. That is a quietly strange thought to sit with. The timescales associated with heat death have also been revised in recent years. For a long time, the final state of the universe was placed at something like 10 to the power of 1,100 years, a number so large it is essentially beyond comprehension, a figure that makes the current age of the universe look like a single breath. But more recent work has brought that estimate down considerably. Some researchers now suggest the universe could reach a truly dead state on the order of 10 to the power of 78 years. Still an almost inconceivable expanse of time. Still billions upon billions of times longer than anything we can meaningfully picture. But vastly shorter than the older estimate. 10 to the power of 78. Written out, that is a 1 followed by 78 zeros. For comparison, the current age of the universe is roughly 10 to the power of 10 years. The difference between those two numbers is the entirety of deep time that still lies ahead, assuming the universe does not collapse first. What is perhaps most striking about all of this is how sensitive these projections are. The timeline to heat death is not a robust, stable prediction. It is extraordinarily fragile. A tiny change in the assumed behavior of dark energy, a small shift in the value of W, a slight variation in how it might evolve, can move the projected end time by many orders of magnitude. We are not talking about adjusting the answer by a few million years, or even a few billion. We are talking about changes that shift the timeline by factors of trillions upon trillions. The uncertainty in our picture of the end is not just large. It is almost incomprehensibly large. And this is what makes the study of cosmological fate so unique among scientific pursuits. In most fields, greater precision leads to a more stable answer. Here, the more carefully we measure, the more clearly we see how much depends on things we cannot yet pin down. Every new dataset refines our picture just enough to show us how intricate the question really is. The universe, it turns out, keeps its final secret well. It gives us just enough information to ask better questions, and then, very calmly, declines to tell us exactly how it ends. There is a certain kind of ending that does not announce itself. No single moment of rupture, no dramatic final event. Just a long, unhurried unwinding, the kind of ending that happens so slowly it is almost indistinguishable from continuation, until one day, almost imperceptibly, everything that once made the universe luminous and alive has simply stopped. That is the ending the evidence currently points toward. Not a collapse. Not an explosion. A fading. And it begins, in cosmic terms, relatively soon, with the stars. Right now, the universe is in what astronomers call the stelliferous era, the age of stars. For roughly the past 13 billion years, stars have been forming in clouds of hydrogen and helium, burning, aging, dying, and seeding the cosmos with heavier elements that would eventually become planets, and oceans, and living things. It is a cycle that has continued so long it can feel permanent. But it is not permanent. It has a budget, and that budget is being spent. The raw material for star formation is gas, vast clouds of it, drifting through galaxies, slowly condensing under gravity into new suns. But that supply is finite, and it is being consumed. Stars burn through hydrogen. When they die, some of that material is returned to space, but not all of it. With each generation of stars, the available gas decreases. Slowly, across timescales of trillions of years, the rate of star formation will decline. Fewer new stars will be born. The ones that remain will age and go dark. And eventually, no new stars will form at all. The universe will not go dark in an instant. It will dim, gradually, the way an ember cools after the fire has gone out. The last stars, small, slow-burning red dwarfs, will persist for trillions of years before they too exhaust their fuel. But the direction is fixed. The age of stars has an end, and we are living in its earlier chapters. What is quietly sobering is that life, at least life as we understand it, life that depends on the stable warmth of a star, may face its own horizon far sooner than the universe faces its. On scales of billions of years rather than trillions, the conditions that allow planets to be habitable, that allow liquid water and stable chemistry and the slow patient work of biology, will become increasingly rare. Stars will evolve. Some will brighten and expand, sterilizing the worlds around them. Others will cool and dim. The window of hospitable conditions for life, across the universe as a whole, may be far shorter than the universe's total lifespan. In the very long view, the era in which life is possible may be a brief and precious interval, already well underway, already aging. Meanwhile, something else is happening, something harder to see but no less consequential. The universe is not just aging from within. It is also thinning from without. Because space is expanding, and because that expansion is accelerating, distant galaxies are moving away from us, not through space, but with space, carried by the stretching of the fabric of the cosmos itself. At great enough distances, galaxies recede so fast that the light they emit can never reach us. They cross what is called the cosmological horizon, and from that point on, they are effectively gone from our universe. Not destroyed. Not collapsed. Simply unreachable forever. This process is already happening. There are galaxies in the universe right now that we can still see, whose ancient light is still arriving, but which we could never reach, even traveling at the speed of light for the rest of time. And there are galaxies whose light will never reach us, because the space between us and them is expanding faster than light can cross it. Over billions of years, more and more of the universe will cross beyond that horizon. The Great Cosmic Web, the vast network of filaments and clusters and superclusters that makes up the large-scale structure of the universe, will dissolve. Clusters will drift apart. The gravitational bonds that hold groups of galaxies together will, in some cases, eventually fail to overcome the relentless pull of expansion. What was once a richly interconnected structure will break down into isolated islands, separated by voids so immense they dwarf anything in the present universe. And for any observer living in that far future, the sky will tell a very different story. The cosmic microwave background, that faint, cool glow of radiation that permeates all of space, the afterglow of the Big Bang itself, one of the most important signals in all of cosmology, will not last forever. It is already extremely cold, just a few degrees above absolute zero, redshifted by billions of years of cosmic expansion to wavelengths far longer than visible light. But the expansion will continue to stretch it. The photons of the CMB will grow longer and longer in wavelength, more and more dilute, until they fall entirely below any threshold of detection. The background hum of the early universe will fade to silence. Future observers, if any exist, will not know it was ever there. And that is perhaps the strangest part of this long unraveling. It is not just that the universe will eventually become cold and dark. It is that, long before that final state arrives, the view of the universe will have already become a shadow of what it once was. Right now, we can observe something like 93 billion light-years across. We can see the structure of the early universe in the cosmic microwave background. We can trace the web of galaxies across vast distances. We can measure the expansion rate and piece together the history of everything. We live at a remarkable moment, perhaps one of the best possible moments, to understand the cosmos in its full complexity. But as expansion continues, that view will shrink. Galaxies will disappear beyond the horizon one by one. The observable universe, paradoxically, will become smaller over time, not larger, even as the total universe continues to grow. Future civilizations, if they exist, will look out at a sky with fewer and fewer galaxies. Over deep time, even the nearest neighbors will eventually recede. There may come an era, unimaginably far away, when the only things visible to any observer are the stars and remnants of their own local group. A small gravitationally bound island, surrounded by absolute darkness in every direction, with no evidence at all that anything else exists or ever existed. No CMB. No distant galaxies. No large-scale structure to measure. No way, from that vantage point, to reconstruct the history of the cosmos. An observer born into that time would have no way of knowing that the universe had once been filled with hundreds of billions of galaxies. No way of knowing about the Big Bang, or the cosmic web, or the billion-year history of star formation. They would see only their small island of light, and infinite darkness beyond it, and would have no reason to suspect that anything more had ever been there at all. We are fortunate, in a way that rarely gets acknowledged, to live at the time we do. At a moment when the evidence is still visible. When the full sweep of cosmic history is still, just barely, readable in the sky. The universe is already, slowly, beginning to forget itself. The information is still there, for now. The light is still reaching us, from a time when the cosmos was young and dense and radiant. But that window is not permanent. The universe will not always be this legible. And so there is something quietly urgent and quietly beautiful about the fact that we are looking. That right now, at this particular moment in the history of everything, there are creatures on a small rocky planet who have built telescopes, and written equations, and trained themselves to read the ancient light falling across the sky, asking questions that no one, and nothing, will be able to ask in quite this way again. When we try to hold the true scale of cosmic time in our minds, something quietly breaks down. Not in a distressing way, more like the feeling of standing at the edge of a very large ocean and realizing that the horizon is not the end of it. The mind reaches outward, and the distance simply does not resolve. The entire span of human history, every civilization, every dynasty, every century of recorded thought and language and art, amounts to roughly 10,000 years. The universe is already 13.8 billion years old. That means all of human history represents something like 1/1400,000th of the universe's current age. A fraction so small it would barely register on any reasonable timeline. And the timescales ahead dwarf even that. The phases of the universe's long decline are measured in units that our language was never built to carry. 1 trillion years. A quadrillion. Numbers so large that the scientific notation used to write them, 10 to the power of some staggering exponent, becomes the only honest way to express them, because writing them out in full would produce pages of zeros that communicate nothing to the reading mind. They are, in a practical sense, beyond comprehension. And yet they are real timescales, as real as yesterday, simply operating at a register the human brain was never required to evolve the ability to feel. So it helps, perhaps, to think of the future not as a single long wait, but as a series of eras, each one nested inside the next, each one defined by what still remains. In the nearer deep future, structure begins to dissolve. Galaxies drift apart. Star formation ends. The last red dwarf stars burn down slowly over trillions of years, and then go dark. This is the end not of matter, but of the large-scale architecture of the cosmos, the shapes and forms that organize the universe into something visually complex and alive. Galaxies, star systems, planets. All of these are temporary arrangements, structures that gravity built and time will eventually dismantle. Long after the last star has faded, what remains is a universe of remnants. Black holes, slowly evaporating over timescales that stretch to incomprehensible lengths. Neutron stars, cold and inert. Rogue planets drifting through absolute darkness with no star to orbit and no warmth to sustain them. The universe in this era is not empty. It is littered with the cold wreckage of everything that once burned. Structure has ended, but matter has not. And matter itself, in some theories, may not be permanent either. Protons, the stable building blocks of atoms, the particles that make up everything from water to rock to the cells in a human body, may eventually decay. Slowly, over timescales so vast they make the stellar era look brief, every atom in the universe may simply come apart. Not through collision or heat, but through the quiet statistical inevitability of quantum processes operating across unimaginable spans of time. If proton decay is real, then the universe loses even its wreckage eventually. What remains after that is a universe of particles and radiation, photons, electrons, neutrinos, and the slow thermal glow of evaporating black holes. The universe does not become nothing. It becomes something thinner and colder than anything we have words for. Temperature is the thread that runs through all of this. As the universe expands, it cools. It has been cooling since the Big Bang, from the unimaginable heat of the first moments, through the warm plasma of the early universe, through the long stellar era, and onward toward a temperature that approaches, but never quite reaches, absolute zero. There is a floor of coldness, a point at which all thermal motion ceases entirely, and the universe is making its way toward it with the patience of something that is all the time that will ever exist. At absolute zero, there is no energy available to do work. No heat to drive any process. No gradient between hot and cold for any engine, biological or mechanical or physical, to exploit. This is what entropy ultimately demands. Not the destruction of energy, but its complete and final equalization. Energy spread so evenly across such an immense volume that no part of the universe is any different from any other part, and nothing can happen, because nothing has anywhere to go. Entropy is the arrow that runs through all of this. The second law of thermodynamics, applied not to a closed room or a steam engine but to the entire universe, says simply that disorder increases. That energy, left to itself, spreads out. That the concentrated, organized, luminous state of the universe, stars and galaxies and warm planets, is a temporary condition, and the cold, uniform, featureless state is the stable one. We live in the brief, brilliant exception. The long rule is stillness. But here is where the story becomes philosophically interesting, because the end of the universe, as physics currently describes it, is not quite what we might imagine when we hear the word ending. There is no final explosion. No moment when a clock strikes zero. No singular event that marks the transition from universe to non-universe. Instead, the end is a process, an overlapping sequence of slower and slower changes, each era bleeding into the next without a clean boundary. The universe does not stop. It asymptotically approaches a state where nothing meaningful happens anymore. And that distinction matters. The final state of the universe, in most current models, is not emptiness in the way we usually picture it. It is not the absence of everything. It is a near emptiness, a vast, cold, almost featureless sea of the lowest energy particles and radiation, spread across a space so enormous that the average distance between any two particles is beyond imagining. Something is still there. It is simply so dilute, so cold, so energetically inert, that no structure, no process, no event can arise from it. Some physicists describe this as an eternal equilibrium. Not a catastrophe, not a collapse, not even a moment of finality, just a state that, once reached, persists forever, because there is nothing left to disturb it. A kind of permanent, infinite sameness. Every direction identical to every other. Every moment indistinguishable from the one before it. This is the version of the end that sits furthest from our intuitions. We tend to imagine endings as events, something happens, and then it is over. But the heat death of the universe is, in a sense, the opposite of an event. It is the cessation of events. History does not end with a final chapter. It simply runs out of things to record, and the last pages are blank, and the blank pages go on forever. There is a strange quality to sitting with that image. Because on one level, it is deeply quiet. There is no suffering in it, no violence. The universe does not end badly. It ends the way a sound ends when it has traveled far enough, not cut off, just gradually beyond hearing, until the silence it leaves behind is total and complete. And yet it also contains something that resists our deepest instinct about what nothing means. The end is not nothing. It is something, just something so thin, so cold, so still, that from the inside, it would be impossible to distinguish from nothing at all. A universe that technically exists, but in which existence has ceased to have any texture. Perhaps the most human response to all of this is simply wonder. Not dread, not despair, but a kind of quiet amazement that the universe is knowable enough for us to trace its likely arc from the first fraction of a second to the last fading warmth of an evaporating black hole. That the equations we have built, painstakingly, across centuries of observation and thought, are powerful enough to sketch even the outline of something this immense. We are not outside the universe, looking in. We are made of it, built from the same matter that was forged in the cores of stars, shaped by the same physical laws that will eventually carry everything to stillness. Whatever the universe is moving toward, we are part of that movement. Small, brief, improbably aware. And for now, the stars are still burning. There is a temptation, when thinking about the long decline of the universe, to imagine it going completely dark, a final blackout, total and absolute. But the physics is more subtle than that, and in a strange way, more interesting. Even in the deepest future, after the last star has gone cold and the last planetary orbit has decayed, the universe will not be perfectly empty. A faint background of photons, particles of light at the lowest possible energies, will persist, drifting through the expanding void. Not enough to illuminate anything. Not enough to warm anything. But present, nonetheless, in the way that the last trace of a sound lingers in a room long after the music has stopped. The universe will approach darkness. It will not quite reach it. But before that near darkness settles in, there is another era. A long one. Perhaps the longest era in which anything recognizable still exists. It is the age of black holes. When the last stars die, they leave behind remnants. The most massive ones collapse into black holes, objects so dense that not even light can escape their gravity, regions where space-time curves so severely that it closes in on itself. Right now, black holes are relatively rare on cosmic scales. They are the endpoints of the most dramatic stellar deaths, scattered across galaxies that are still mostly filled with living stars. But as the stellar era winds down and the stars go dark one by one, the balance shifts. The black holes remain. And slowly, across trillions of years, they come to dominate the universe. There will come a time when the most common large objects in the cosmos are not stars or galaxies as we know them, but black holes, massive, silent, invisible against the darkness, orbiting one another or drifting alone through the void. The universe in that era is not entirely inert. Black holes still interact gravitationally. They still merge, occasionally, releasing gravitational waves that ripple outward through empty space with no one to detect them. They are the last large structures, the final inheritors of all the matter that ever burned and all the stars that ever existed. And then, very slowly, even they begin to go. In 1974, Stephen Hawking made one of the most remarkable theoretical predictions in the history of physics. Black holes, he showed, are not perfectly black. They emit a faint thermal radiation, so faint that for any black hole of stellar mass or greater, it is entirely negligible compared to any other process in the universe. But it is real, and it has a consequence that plays out over timescales almost beyond expression. Given enough time, a black hole will radiate away all of its mass and simply cease to exist. This is called Hawking radiation, and it means that black holes are not permanent. They are, in the vocabulary of physics, metastable, stable enough to last for incomprehensible spans of time, but ultimately temporary. A black hole the size of the Sun would take around 10 to the power of 67 years to evaporate completely. The supermassive black holes at the centers of galaxies, millions or billions of times more massive, would take vastly longer. Some estimates place the evaporation time for the largest black holes at around 10 to the power of 100 years. That number has a name, a googol. And it sits so far beyond anything in ordinary experience that it functions less as a quantity and more as a symbol of the depth of time the universe still has in front of it. The end times of the universe are, in a very real sense, calibrated on these black hole lifetimes. When cosmologists speak of the final eras of cosmic history, they often use the evaporation of the last supermassive black holes as a kind of anchor, a marker for when the last significant structures will finally dissolve. Everything before that point is prelude. But the universe does not wait idly for its black holes to finish. Other things are happening, on their own extraordinary timescales. Neutron stars, the ultra-dense remnants of stars that were not quite massive enough to form black holes, will not last forever either. Quantum mechanical processes, operating over timescales far longer than any nuclear or chemical reaction, may eventually destabilize them. They will not explode or collapse. They will simply, over unimaginable time, convert to more stable configurations, or dissolve. The smaller black holes will evaporate well before the giants. The universe will shed its remnants in order of their resistance to time, each one holding on as long as physics allows before finally letting go. And if the proton, that remarkably stable building block of all ordinary matter, is not truly stable, then something even more profound happens. Every atom in the universe, every grain of matter that was not swept into a black hole, will eventually decay. Not through any collision or violent event, but through the same quiet statistical inevitability that governs all quantum processes. Given enough time, even the most stable particle eventually finds a lower energy state. If protons decay, Then over timescales on the order of 10 to the power of 40 years or more, all ordinary matter in the universe dissolves. Rocks, cold planets, the frozen remains of dead stars, all of it, slowly and silently, coming apart at the atomic level, leaving behind only the lighter particles and radiation that the decay products become. Even the white dwarfs, those dense, cooling remnants of stars like our own sun, objects that can persist for trillions of years without any fuel at all, may not be permanent. There is a quantum mechanical process called tunneling, by which particles can cross barriers that classical physics would say are impassable. Over extraordinary timescales, quantum tunneling could cause the matter inside a white dwarf to rearrange itself, effectively allowing the star to change its structure or composition without any external energy input. Given enough time, white dwarfs too may dissolve into something simpler and more stable, their material quietly reorganizing into the lowest energy form available. Time, in the deep future, is not just a passive backdrop. It is an active force. Given enough of it, even the most improbable processes become inevitable. And then there are what some physicists have called the last fireworks. As black dwarfs, the final cold remnants of white dwarfs, objects that have cooled over trillions of years to near absolute zero, age across timescales of 10 to the power of 1,100 years or longer, something unexpected may happen. Quantum tunneling, that same strange probabilistic process, could cause nuclear reactions deep within these ancient stellar corpses. Reactions that would not occur under any normal circumstances, but that become statistically unavoidable given enough time. These reactions could trigger a supernova, a full stellar explosion, from a star that has been dark and cold for longer than the current age of the universe multiplied by itself, over and over, beyond any human frame of reference. These would be the last supernovae in the universe. Not the dramatic, bright explosions we see today, seeding space with heavy elements and lighting up galaxies with their brief intensity. These would be lonely events, each one occurring in a universe so vast and so dark that the light from the explosion might travel for unimaginable distances without ever encountering another object. A flash in a void so complete that the word void barely covers it. And yet it would happen. Physics, patient and indifferent, carrying out its processes regardless of whether anything is there to witness them. What is remarkable about all of this, the Hawking radiation, the proton decay, the quantum tunneling, the black dwarf supernovae, is that none of it requires any new physics. These are all consequences of well-established principles, extended honestly into the deep future. The universe does not need to do anything extraordinary to arrive at these states. It simply needs to keep doing what it is already doing, for long enough. Time, in sufficient quantities, is the most powerful force in the cosmos. More powerful than gravity, more powerful than nuclear fusion, more powerful than any explosion. Given enough of it, even a black hole fades. Even a proton decays. Even the cold, inert remnants of the last dead stars eventually find a way to burn, one final time, in the dark. The universe's last light will not come from a living star. It will come from something very old, and very quiet, finally letting go of the last energy it had been holding onto since before recorded history was a thought in any mind that ever existed. And after that, the long patience of the dark era settles in. The near emptiness that is not quite nothing. The faint background hum of the lowest energy photons, drifting through a space so cold and so still that the word silence does not begin to describe it. The universe, at that point, will have been doing this, existing, expanding, cooling, for so long that the entire history of stars and galaxies and life and thought will be, by comparison, a brief bright flicker at the very beginning of everything. A moment of warmth and complexity and light, surrounded on all sides by an immensity of quiet time. And somehow, in the middle of that flicker, here we are. Long after the last star has gone dark, long after the last black hole has finished its slow evaporation, the universe will still not be entirely silent. The final detectable events in the cosmos may not be bursts of light, or the collapse of matter, or even the faint thermal glow of Hawking radiation. They may be something far more subtle. Gravitational waves, ripples in the fabric of spacetime itself, generated by the last mergers of the last massive objects, could persist as the final signals in an otherwise empty universe. Not light, not sound, just the geometry of space, trembling faintly from the last great collisions, propagating outward through a void with nothing left to absorb them. It is a strange and quietly beautiful image. The last message the universe sends is not visible. It is structural. A distortion of space itself, traveling forever through a cosmos that has nothing left to say. Computer simulations of the deep future add another layer of texture to this picture. Even near the very end of the universe's active era, the models suggest things are not perfectly smooth or uniform. Tiny structures persist, small clumps of dark matter, gravitationally bound remnants too insignificant to do anything but exist, drifting through the dark. The universe does not achieve perfect homogeneity easily. Even as it approaches its final state, there are wrinkles and irregularities, small departures from the featureless equilibrium it is slowly converging toward. The end, it turns out, is a little messy. Reality clings to complexity longer than our intuitions might expect. And that observation points towards something worth pausing on. Because there is a distinction, an important one, between the end of complexity and the end of matter itself. Matter, in some form, may persist for extraordinary timescales. Particles endure long after any structure they could be part of has ceased to exist. But complexity, the kind of organized, layered, information-rich arrangement that produces galaxies, and ecosystems, and thoughts, that ends far sooner. The universe loses its complexity long before it loses its matter. Structure is fragile. It requires energy gradients, and temperatures above absolute zero, and the right conditions for processes to occur. When those conditions are gone, complexity dissolves, even if the underlying particles linger. There is a curious footnote to this, one that sits somewhere between physics and philosophy. The arrangement of matter in a human body, the specific, intricate organization of atoms and molecules that constitutes a person, is, in principle, just an arrangement. And arrangements of matter, in theory, can persist without life. The atoms themselves are not alive. The pattern is. So in a purely technical sense, matter configured in a human-like shape could outlast the stars, sitting cold and inert in the dark, chemically intact but utterly lifeless, for as long as the material itself holds together. It is not a comforting image, but it illustrates something real. Matter does not know it is dead. The universe carries the remnants of complexity long after complexity itself has ended. But the deeper strangeness begins when we follow the physics not just to the end of structure, but to the end of time itself. In a universe approaching maximum entropy, one in which energy is spread as evenly as it will ever spread, and nothing of significance is changing anywhere, what does time actually mean? Time, as we experience it, is directional. It moves from past to future, causes precede effects. Memories accumulate in one direction and not the other. This asymmetry, what physicists call the arrow of time, is deeply connected to entropy. Time feels like it moves forward because entropy is increasing, because disorder grows, because the universe is always, at every moment, slightly more spread out and disorganized than it was a moment before. But in a maximum entropy universe, entropy has nowhere left to go. It has reached its ceiling. And if entropy is no longer increasing, the arrow of time loses its foundation. There is no thermodynamic reason for one moment to follow another in any particular order. The distinction between before and after begins to dissolve. This is not just a poetic description. It is a genuine problem in the physics and philosophy of time. Some models describe the final state of the universe as effectively atemporal, not frozen in the way a photograph is frozen, but genuinely without the structure that makes time meaningful. A state in which the concept of sequence no longer applies. Not a moment that lasts forever, but a condition in which the word moment has ceased to describe anything real. In such a state, causality itself may unravel. Physical interactions require that one event can influence another, that a cause produces an effect, that information travels from one place to another and changes something. But in a universe cold enough and sparse enough, even these basic interactions become vanishingly rare. The last era of the universe may be one in which physical events are so infrequent that causality exists only in the most theoretical sense, waiting in unimaginable time between each expression of itself. The universe does not violently discard its laws. It simply reaches a condition in which those laws have almost nothing left to operate on. And yet physics suggests that even here, at the apparent end of everything, something may remain. In quantum mechanics, information is treated as something fundamental. The quantum state of a system, the full description of what it is and how it is entangled with everything around it, is not so easily destroyed. There is a principle, debated but widely held, that quantum information cannot be truly annihilated. It can be scrambled, dispersed, rendered inaccessible to any practical observer, but it is not gone. It persists, encoded in correlations and entanglements that spread across the universe as matter and energy interact and decay. This means that the very far future of the universe may be a place where the dominant remaining structure is not matter, and not radiation, but information, subtle quantum correlations between particles and fields, a web of entanglement that carries the imprint of everything that ever happened, in a form so diluted and scrambled that nothing could ever read it, but present nonetheless. Some physicists have speculated that even after matter has dissolved and the last black holes have evaporated and the final faint photons have spread to wavelengths longer than the observable universe, there may remain a residual background of quantum information, a kind of cosmic memory, written in the entanglement structure of the void itself. Not accessible, not interpretable. But there. The universe, on this view, does not truly forget. It encodes everything that ever happened, every star that ever burned, every particle collision, every moment of any kind that ever occurred anywhere, leaves a trace in the quantum state of the universe, preserved in a form that nothing will ever read again. There is something in that idea that resists easy summary. It is not comforting in any ordinary sense. The information is not recoverable. The memory is not a memory in any meaningful way. And yet there is something that feels significant about the possibility that the universe does not simply erase its history, but carries it forward, folded into the deepest structure of what remains. The end of the universe, on the longest timescales, may not be an emptying but a kind of translation. Matter becomes energy. Energy becomes radiation. Radiation redshifts toward silence. Structure dissolves into particles. Particles decay into lighter particles. And beneath all of it, persisting past every other form, an abstract record of the full complexity that once existed, encoded in the entanglement of things that no longer have names, drifting through a space that no longer has a meaningful sense of time. It is, in its way, the strangest library that has ever been imagined. Holding everything, readable by nothing, lasting longer than anything else in the universe. And the universe continues, in this sense, to hold its history inside itself, the way a person sometimes holds a memory not by thinking of it consciously, but simply by being shaped by everything that came before. The past does not vanish. It becomes the texture of what remains. Physics, at its deepest level, is a science of what persists. Of what cannot be destroyed, only transformed. And when you follow that thread all the way to the end of the universe, you arrive at questions that sit right at the boundary between physics and philosophy, questions about whether anything is truly final, and whether an ending, in the deepest sense, is even possible. One of the more striking ideas in modern theoretical physics concerns quantum entanglement, the phenomenon by which two particles can share a connected quantum state, such that measuring one instantly affects what can be known about the other, regardless of the distance between them. Entanglement is not just a curiosity of particle physics. Some researchers believe it may be woven into the structure of spacetime itself, that the geometry of space, the very fabric that gives the universe its shape, may emerge from the entanglement relationships between quantum degrees of freedom at the most fundamental level. If that is true, then what happens as the universe approaches its final state takes on a new dimension. As matter decays and particles become increasingly isolated from one another, entanglement between distant parts of the universe could weaken. And if entanglement is what holds the geometry of spacetime together, then its gradual dissolution might not just be a consequence of the universe's ending, it might be part of the mechanism. Spacetime itself, in this picture, does not simply persist as an empty stage after all the actors have left. It may gradually lose coherence, its geometry becoming less well-defined as the quantum correlations that underpin it thin out. The universe's ending, at the deepest level, could be the dissolution of the structure that makes location and distance meaningful in the first place. And yet even in this near-total emptiness, quantum mechanics ensures that the universe is never quite completely still. Quantum fluctuations, the brief, spontaneous appearance of particle-antiparticle pairs from the vacuum, are a fundamental feature of quantum field theory. They happen constantly, everywhere, because the vacuum is not truly empty. It has energy, and that energy fluctuates. In the early universe, these fluctuations seeded the density variations that eventually grew into galaxies. In the far future, they will continue, long after any other process has ceased. Tiny pairs of particles flickering into existence and annihilating almost immediately, creating a faint irreducible activity in the void. Not enough to build anything. Not enough to reverse the approach toward equilibrium. But enough to ensure that the universe, even at its most desolate, is never in a state of absolute, perfect stillness. The cosmos hums at the lowest possible frequency, forever. There's also a more abstract limit that some physicists have considered. The universe processes information. Every interaction between particles is, in a sense, a computation. Energy and information are deeply connected, and there may be a finite total amount of meaningful computation the universe can perform before it reaches a state where no further information processing is possible. Not a moment in time when a counter reaches zero, but a cumulative limit, a point at which the universe has, in some precise sense, done all the thinking it will ever do. After that, change continues in a purely mechanical sense, but nothing that could be called meaningful transformation occurs again. It is a strange kind of ending. Not darkness, not silence, but the exhaustion of significance. Some of the universe's final information, certain theories suggest, may not be floating freely in space at all. It may be locked inside black holes. The interior of a black hole is, in a deep sense, hidden, cut off from the rest of the universe by the event horizon, the boundary beyond which nothing can escape. What happens to information that falls in is one of the central unsolved problems in theoretical physics, known as the black hole information paradox. Does that information survive in the Hawking radiation that eventually carries the black hole's mass away? Is it encoded on the event horizon in some scrambled form? Or is it genuinely lost? The answer matters enormously for the question of the universe's final state. If information is preserved in Hawking radiation, then everything that ever fell into every black hole that ever existed is, in principle, still present in the universe, just extraordinarily scrambled. If it is lost, then the universe has already been erasing its own history, and will continue to do so until the last black hole is gone. There is also a deeper epistemic problem lurking here, one that is easy to state and impossible to resolve. The true final state of the universe may be unknowable, not just in practice, but in principle. Because we are observers embedded inside space-time, we can only ever access information that reaches us along causal pathways, light or signals that travel through space to arrive at our location. But in a universe where space-time itself may be dissolving, where causal connections are becoming vanishingly rare, where the observable horizon is shrinking, there may be no vantage point from which the true final state is visible. Any observer, however advanced, is always inside the universe, always limited by what can physically reach them. The ending, if there is one, may occur in regions of the universe that are simply and permanently beyond any possible observation. Some holographic theories of physics suggest that the real information content of the universe is not stored in its three-dimensional volume at all, but on a kind of two-dimensional boundary, a surface that encodes everything happening inside. In this framework, the true ending of the universe might not be an event you could watch from inside spacetime. It might be a transformation of the boundary structure, a change in the holographic encoding that underlies reality, invisible to anyone living within the projection it generates. The ending would be real and total and completely hidden. These are the strange territories that physics enters when it takes seriously the question of ultimate endings. But not all of the universe's possible endings are quiet ones. The scenarios described so far, heat death, gradual dissolution, the slow evaporation of the last black holes, share a common character. They are slow. They are patient. They take place over timescales so vast that the word gradual barely captures them. But physics also allows for endings that are sudden, violent, and total. Endings that would not wait for entropy to do its quiet work. One of them is the Big Crunch. If dark energy, rather than staying constant or growing, were to weaken and eventually reverse, becoming negative, effectively, then the expansion of the universe would slow, halt, and reverse. Gravity would begin to win. The great recession of the galaxies would stop and turn around, the universe contracting back on itself, growing hotter and denser as everything rushed inward. Galaxies would merge. Stars would collide. The cosmic microwave background would blue shift back to visible light, then to ultraviolet, then to X-rays, bathing the entire universe in lethal radiation long before the final collapse. The end would not be cold and quiet but hot and catastrophic, a mirror image of the Big Bang, everything compressed back into a singularity of unimaginable density. Current observations do not favor this scenario. The expansion of the universe appears to be accelerating, not decelerating. But dark energy is poorly understood, and if it evolves over time, all bets are open. A second violent possibility is the Big Rip. This is the scenario in which dark energy does not stay constant, but grows stronger over time. In this case, the accelerating expansion does not merely push galaxies apart, it eventually becomes powerful enough to overcome every other force in nature, one by one. Gravitational bonds between galaxies fail first. Then the gravity holding individual galaxies together. Then the gravity holding star systems together. Then the electromagnetic forces holding planets together, then molecules, then atoms. In the final moments before the Big Rip, the fundamental forces of nature are overwhelmed by the expansion of space itself, and matter at every scale is pulled apart. Atoms are dismembered. Protons and neutrons are separated. And then, in the last fraction of a second, space-time itself is torn. The Big Rip would not require trillions of years. If dark energy strengthens sufficiently, it could arrive in a finite, though still vast, amount of time. Everything, everywhere, simultaneously undone. And then there is perhaps the strangest of the violent endings. The vacuum decay catastrophe. The vacuum of space, the lowest energy state of all the quantum fields that fill the universe, may not be the truly lowest possible state. There may be a deeper vacuum, a more stable configuration of those fields, that our universe has not yet reached. Our current vacuum would, in that case, be what physicists call a metastable state, stable enough to persist for an enormously long time, but not permanently stable. Like a ball resting in a small valley partway up a hill, rather than at the bottom. If a quantum fluctuation, anywhere in the universe, were to knock the vacuum into this lower state, it would trigger a bubble of true vacuum, a region where the laws of physics are fundamentally different, that would expand outward at the speed of light. There would be no warning. The bubble wall, moving at the maximum possible speed, could not be preceded by any signal. One moment, the laws of physics are as they always were. The next moment, they are not. Every structure, every particle, every force, every constant of nature, instantly and permanently rewritten. Not destroyed in any conventional sense, but converted into something so different that the word universe would no longer apply. No one would see it coming. Nothing would survive it. And nothing that occurred within the bubble would bear any resemblance to anything we understand. What is striking about all three of these violent endings is that they are not ruled out. They are not scientific fiction. They are legitimate possibilities, consistent with current physics, kept at bay only by the particular values that dark energy and the vacuum happen to have, values that we cannot yet predict from first principles, and that could, in principle, be different from what observation currently suggests. The universe is not guaranteed a gentle death. It has the option of a violent one. And it has not told us, definitively, which it has chosen. That uncertainty is not a failure of science. It is an honest acknowledgement of how much remains unknown about the deepest nature of the cosmos. We are reading the universe as carefully as our instruments allow, and we are doing remarkably well. But the universe is not obligated to stay within the boundaries of what we currently understand. It reserves the right to surprise us. There is a category of ending that does not require billions of years of patient decline. It does not need entropy to do its slow work, or black holes to gradually evaporate, or matter to quietly decay across unimaginable timescales. It requires only one thing, that the universe is not quite as stable as it appears. The idea begins with a concept that sounds almost mundane until you follow it to its conclusion. Phase transitions are familiar events. Water freezing into ice is a phase transition. Steam condensing into liquid is a phase transition. The material does not change its fundamental identity, but its structure reorganizes into a lower energy configuration, and that reorganization releases energy, and happens quickly, and cannot be undone. Now apply that idea not to water, but to space itself. The vacuum of the universe, the ground state of all the quantum fields that fill reality, may not be at the lowest possible energy. It may be sitting in what physicists call a false vacuum, a configuration that is stable enough to persist for an enormously long time, but not the most stable configuration available. Beneath it, in the landscape of possible physics, there may be a true vacuum, a deeper, lower energy state that our universe has not yet settled into. If that is the case, then the universe is, in a sense, balanced on a ledge. Not a precarious one. The ledge may be so stable that it could persist far longer than the current age of the universe. But ledges, given enough time in quantum mechanics, do not hold forever. A quantum fluctuation, unpredictable, unavoidable, could, somewhere in the cosmos, nudge the local vacuum state over the edge and into the lower configuration. And from that point, a bubble of true vacuum would expand outward at the speed of light, carrying with it a completely different set of physical laws. Inside that bubble, the constants of nature are different. The masses of particles, the strengths of forces, the rules governing how matter and energy interact, all of it rewritten. Not gradually, not partially. Completely. Everything the universe has built over 13 billion years, every galaxy, every star, every atom, would be instantly and permanently converted into something that bears no resemblance to what came before. And because the bubble expands at the speed of light, nothing can outrun it. No signal, no warning, no last observation. The boundary arrives at exactly the speed at which information could possibly announce its coming. You would not know it had happened. There would be no moment of awareness, no transition experienced from the inside. The old laws of physics simply stop applying, and the new ones take their place, and anything that existed under the old laws does not continue to exist under the new ones. It is, in the most literal sense, the end of everything as we know it. And it could happen tomorrow, or in 1 trillion years, or never. We do not know which. The Higgs field sits at the center of this particular concern. The Higgs field permeates all of space and gives mass to fundamental particles. It has a specific value, a specific energy state, that it settled into early in the universe's history. But calculations based on the measured mass of the Higgs boson suggest that this state may be metastable. That the Higgs field could, in principle, tunnel quantum mechanically into a lower energy configuration. And if it did, the consequences would be precisely what vacuum decay describes, a bubble of altered physics, spreading at the speed of light, restructuring reality as it expands. Current measurements place us in a range that physicists describe as being on the edge between stability and metastability. The universe, according to these calculations, is either safely stable or just barely not. The uncertainty in the relevant measurements is large enough that we cannot say definitively which side of the line we sit on. It is one of the more quietly unsettling facts in modern physics, not because collapse is imminent or even likely in any human-relevant time frame, but because we genuinely do not know whether the ground beneath all of physics is solid or subtly hollow. Beyond vacuum decay, there are other ways the universe's ending might be tied to the deep structure of its fields and forces. The fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, are, in the modern understanding of physics, different aspects of underlying fields and symmetries. In the very early universe, some of these forces were unified, indistinguishable from one another, only separating into distinct forces as the universe cooled and underwent a series of symmetry-breaking transitions. What if the universe is not done breaking symmetries? What if the current arrangement of forces and fields is not the final one, but another temporary configuration, stable for now, but subject to further transitions as the universe evolves? A cosmic phase transition of this kind might not be as violent as vacuum decay. It could, in principle, be smoother, a gradual reorganization of the universe's fundamental structure into a new configuration, one that might allow some forms of physics to continue while others cease entirely. Or it might be sudden and total. The outcome would depend on the nature of the transition, and we do not have the theoretical tools to predict it with confidence. There is also the question of dimensions. The universe we experience has 3 spatial dimensions and 1 dimension of time. But certain theoretical frameworks, particularly string theory and its relatives, suggest that there may be additional spatial dimensions, compactified or curled up at scales far smaller than any current experiment can probe. These extra dimensions are not idle mathematical decorations. They have energy. They have geometry. And in some models, they can evolve. If the extra dimensions of space were to change, to uncurl, to expand, to shift their geometry, the consequences for the physics of our 3-dimensional universe could be profound. The effective constants of nature in our dimensions depend on the configuration of the extra dimensions. A change in that configuration could alter the masses of particles, the strengths of forces, the structure of space itself. In some brainworld models, our universe exists as a membrane, a brain, floating in a higher dimensional space alongside other brains. And if 2 brains were to collide, the energy released would be catastrophic on a universal scale. Some cosmologists have proposed that such a collision might even be responsible for the Big Bang, that what we call the beginning was actually a collision between brains, which raises the unsettling implication that it could happen again. These ideas are speculative. They are not confirmed by experiment. But they are mathematically consistent and actively studied, and they illustrate how many different ways the universe's ending might be tied to features of reality that we have not yet directly observed. What is perhaps most interesting is that some of these questions, particularly those surrounding vacuum stability, may be partially answerable by experiment. Particle colliders, by probing the properties of the Higgs field and other fundamental particles at higher and higher energies, are effectively mapping the landscape of vacuum stability. Future accelerators, more powerful than anything currently built, could measure the relevant parameters precisely enough to determine whether our vacuum is truly stable or metastable. The question of whether the universe will end in a vacuum decay catastrophe may, in principle, be something we can make progress on in a laboratory. That is a remarkable thing. The fate of the universe, written into the precise mass of a particle, readable in the data from a machine we can build. Dark energy also enters the picture here in a subtle way. If dark energy is not a fixed constant but a dynamical field, one that fluctuates and evolves, then its tiny quantum variations over cosmological timescales could slowly steer the universe toward one outcome or another. Not dramatically, not suddenly, but through the accumulation of small influences over unimaginable spans of time. The long-term fate of the cosmos may be partly a statistical process, shaped by the quantum noise of the field that dominates the universe's energy budget. Small fluctuations, compounded across trillions of years, gradually nudging the trajectory. And all of this, the vacuum decay calculations, the Higgs field stability analysis, the brain-world collision models, the extra-dimension dynamics, exposes something important about the limits of our current theories. Quantum gravity is the name we give to the as-yet undiscovered theory that unifies quantum mechanics with general relativity. We needed to describe the very early universe, the interior of black holes, and the ultimate fate of space-time. And every time physicists try to push their calculations to the extreme limits of cosmic time, to the very end of the universe's story, they run into the boundaries of what existing theories can handle. The equations break down. The approximations fail. The results become ambiguous or inconsistent. In this sense, the question of how the universe ends is not just an exercise in applying known physics to extreme conditions. It is a diagnostic tool. A stress test that reveals, with unusual clarity, exactly where our deepest theories are incomplete. The end of the universe is where the edges of human knowledge become most visible, where the map runs out, and beyond which there are only the honest words, "We do not yet know." That not knowing is not a dead end. It is a direction. Every gap in our understanding of the universe's fate is pointing toward a piece of physics we have not yet discovered. The questions the end raises, about vacuum stability, about the nature of dark energy, about quantum gravity, about the fate of information, are some of the most active and productive questions in theoretical physics today. The end of the universe is not just a distant event to be passively awaited. It is a problem to be worked on, one equation and one observation at a time, by a species that has barely begun to understand the cosmos it finds itself in. And that, in its own quiet way, is one of the most extraordinary things about being here. Every ending carries, somewhere inside it, the question of what comes next. It is a question human beings have asked about death, about civilizations, about the seasons, and it turns out we ask it about the universe too. Not just out of hope, but out of genuine mathematical curiosity. Because the equations of physics, pushed to their limits, do not always point to a final, permanent ending. Sometimes they point to something else entirely. The idea of a cyclic universe, a cosmos that does not simply end, but transforms, and begins again, is not new. Cultures across history have imagined time as a wheel rather than a line. What is new is that modern physics has found ways to make that intuition mathematically precise, to ask not just whether cycles are poetically appealing, but whether they are physically possible. The simplest version of the idea is called the big bounce. In a universe heading toward a big crunch, collapsing inward under its own gravity, growing hotter and denser as everything rushes together, classical physics predicts that the collapse ends in a singularity, a point of infinite density where the equations break down and the laws of physics, as we know them, cease to apply. But classical physics may not be the right tool for that regime. At the scales involved in a collapsing universe, quantum effects become important. In quantum gravity, the framework we do not yet fully have, but are working toward, may change what happens at those extremes. Some models of quantum gravity suggest that instead of a singularity, the collapse reaches a maximum density and then rebounds. The quantum pressure of the compressed fields and particles, at some critical threshold, becomes strong enough to reverse the contraction. The universe bounces. What was a big crunch becomes, from the other side, a big bang, a new expansion, a new era, a new universe emerging from the compressed remnant of the old one. If this is possible, then our Big Bang may not have been the beginning of everything. It may have been a rebound from the collapse of a previous universe. And that universe may have bounced from one before it. The chain could extend indefinitely in both directions, an eternal series of cosmic cycles, each one a universe in its own right, each ending feeding into the next beginning. No first moment. No final moment. Only the ongoing rhythm of collapse and expansion, compression and release, stretching across a time that has no edges. This picture changes something fundamental about how we think about the question we began with. It reframes the end of the universe not as a terminus but as a transition. Not the closing of a story, but the turning of a page. Quantum loop cosmology, one of the leading approaches to quantum gravity, provides a concrete mathematical framework in which a big bounce is not just speculative but a natural consequence of the theory. In loop quantum cosmology, space is not continuous but made of discrete units, a kind of quantum granularity at the smallest scales. When a collapsing universe reaches the scale at which this granularity becomes relevant, the quantum geometry resists further compression and generates a repulsive effect that drives expansion. The singularity is replaced by a bounce. The new universe that emerges carries some imprint of the one that preceded it, encoded in the quantum state that passed through the transition. But there is another cyclic model that approaches the question from a completely different direction, and it is one of the most elegant and unconventional ideas in modern cosmology. It comes from the mathematician and physicist Roger Penrose, and he calls it conformal cyclic cosmology. Penrose's proposal begins with an observation about the very far future of the universe. In the heat-death scenario, as the universe expands and cools and all massive particles decay, what remains is a universe of massless particles, photons, and perhaps other zero-mass fields, drifting through an ever-expanding space. And here is the key insight: massless particles do not experience time in the way that massive particles do. For a photon traveling at the speed of light, there is no elapsed time between emission and absorption, regardless of how far it travels. A universe populated only by massless particles is, in a deep mathematical sense, scale-free. It has no meaningful notion of size, because there is nothing left that has a fixed scale to compare distances to. In that condition, Penrose argues, the remote future of the universe and the hot, dense state just after the Big Bang share a mathematical similarity. Both are, in the relevant sense, conformally equivalent. The geometry of the far future can be smoothly matched to the geometry of a new Big Bang. One aeon, one cycle of cosmic history, flows directly into the next, not through a violent collapse, but through a quiet mathematical continuity. The end of one universe is literally the beginning of the next, connected not by a bounce but by a smooth geometric transformation. What makes conformal cyclic cosmology particularly compelling to many physicists is that it makes a testable prediction. If previous eons existed, the events in them, particularly the mergers of supermassive black holes, which would have released enormous amounts of gravitational energy, should have left subtle imprints that survive the transition between eons and appear as faint, concentric circular patterns in the cosmic microwave background. The CMB, in this model, is not just a record of our own Big Bang, but a palimpsest, a surface that has been written on before, carrying ghostly traces of the universe that came before ours. Searches for these patterns have produced intriguing but inconclusive results. Some researchers claim to have found hints of them. Others argue the signals are within the range of statistical noise. The question remains open, and the search continues. There is a broader possibility that these cyclic models gesture toward one that is harder to frame as a single theory, but that runs through many of the most ambitious ideas in modern cosmology. It is the possibility that space-time itself is eternal. Not in the sense that our particular universe lasts forever, but in the sense that the underlying structure of reality, the capacity for space and time and physical law to exist, never truly ends. What we call universes may be temporary configurations of something more permanent. Phases, in the thermodynamic sense, that arise and dissolve while the substrate beneath them persists. Some models suggest that our observable universe is not even the primary object in this picture. That what we can see, the 93 billion light-year bubble of space that our telescopes can access, is a remnant. A surviving fragment of something much larger, much older, something whose main structure has long since evolved into a different phase. One of the more striking versions of this idea has been called the dead universe theory. The proposal is that our cosmos may be a pocket, a bubble, that formed within a much older, larger universe, one that itself has already ended or transformed. Our universe, in this picture, is not a first-generation cosmos. It is a child universe, born from the physics of its parent, inheriting some of its properties while departing from others. The universe we inhabit may be, in the deepest sense, a remnant, a local exception to a larger stillness, a region where conditions happen to allow structure and complexity and time to unfold. If this is true, it rewrites the story of time in a profound way. The history of our universe, the 13.8 billion years from our Big Bang to the present moment, is not the whole story. It is an episode. A chapter in a larger narrative that extends far before our beginning and will continue, in some form, far after our ending. Our cosmic history does not sit at the center of time. It sits somewhere in the middle of something much older, embedded in a larger context that our observations, confined to our own causal bubble, cannot directly access. There is something both humbling and quietly expansive about this possibility. Humbling, because it suggests our universe is not the primary fact about reality. Expansive, because it opens a space of possibility in which endings are not endings at all, in which the universe's story does not conclude, but continues in forms we cannot predict and may never observe. What all of these models share, the Big Bounce, conformal cyclic cosmology, the dead universe scenario, the eternal space-time, is a refusal to treat the end as truly final. Each one finds, in the mathematics of the apparent ending, a door rather than a wall. A transformation rather than a termination. Whether any of them are correct is a question that physics is still working toward. Some make testable predictions, and those predictions are being tested. Others remain at the frontier of speculation, waiting for the theoretical tools that would make them fully rigorous. The honest answer is that we do not yet know whether the universe ends or cycles, whether our Big Bang was the first or one of many, whether time itself is finite or eternal. But the fact that these questions can be asked seriously, that the mathematics allows for them, that observations might one day distinguish between them, is itself a kind of answer. It tells us that the universe is stranger and deeper and more generative than any single story about it can capture. And perhaps that is the most fitting thing to carry into the quiet that these ideas invite. Not a conclusion, but an openness. The universe has been here for 13.8 billion years, and by almost any measure, it is still very young. Whatever comes next, whether it is a long cold fading, or a violent tearing, or a quiet bounce into something new, there is an enormous amount of time still ahead. An almost incomprehensible amount of universe still to be. We are here at the very beginning of the long story. Awake just long enough to wonder how it ends. The universe, in many of the models physicists work with, is not the only universe there is. This is not a casual claim, and it is worth sitting with the full weight of it. In the many worlds interpretation of quantum mechanics, every quantum event, every point at which reality branches into multiple possible outcomes, produces not a single result but all of them, each playing out in a separate branch of a constantly ramifying structure. What we call our universe, in this framework, is one branch among an inconceivable number. A single thread in a fabric of staggering complexity, each thread a complete and coherent history, unaware of the others. If this interpretation is correct, then the ending of our universe is not the ending of everything. Other branches continue. Other versions of reality, diverging from ours at every quantum fork in the road, carry on their own histories, perhaps heading toward different fates, perhaps governed by slightly different effective physics, perhaps lasting longer or ending sooner than our own branch. Our cosmic death, in this picture, is a local event. A single candle going out in a room full of candles. There is a quality to that idea that is difficult to name. It does not make the ending of our universe less real or less significant. But it situates it differently, as one event among an uncountable multitude, in a structure of reality so vast that the word everything no longer means what we intuitively think it means. What is equally striking is that even as our universe approaches its end, by whatever mechanism physics ultimately reveals, it may retain certain geometric properties all the way to the last. Right now, the universe appears to have no center and no edge. There is no special point in space from which everything else is equidistant. There is no boundary where the universe ends and something else begins. Every location in the universe is equivalent to every other location in terms of the large-scale structure of space. This property, homogeneity and isotropy at the largest scales, is one of the most fundamental features of the cosmos as we observe it. And there is no reason to expect it to change. A universe expanding toward heat death, or collapsing toward a big crunch, or fading through the slow evaporation of its last black holes, would not develop a center or an edge in the process. The geometry would change, the distances between things would grow or shrink, but the essential character of space, its edgelessness, its centerlessness, would persist. The universe would end the way it has always been, equally, everywhere, all at once. Not converging on a point, not draining toward an edge, just becoming uniformly something other than what it was. This connects to a deeper idea in quantum cosmology, one associated with the work of physicists Stephen Hawking and James Hartle. In what is called the no-boundary proposal, the universe is described in a way that eliminates the concept of a sharp beginning or a sharp end. In ordinary experience, time has edges, a moment before which nothing existed, and presumably a moment after which nothing will. But the no-boundary model treats time as something that smoothly fades out at the extremes, the way the surface of the Earth fades into the poles without ever hitting a wall. There is no first moment in this picture, because time itself becomes less time-like as you approach the beginning or the end, gradually transitioning into a spatial dimension. The universe does not start or stop. It simply has no boundary. This is a mathematically precise proposal, not merely a philosophical metaphor. And it suggests a universe whose ending is not a catastrophe or a wall, but a smooth and gentle limit, a mathematical exit from the regime in which physics as we know it applies, approached asymptotically, without drama. The universe, on this view, does not end. It completes. There is also the possibility that the universe's final state is not a chaotic dispersal of remnants but something more orderly. Certain quantum cosmological models suggest that the cosmos might settle, over extraordinary timescales, into what is effectively its ground state, the lowest energy quantum configuration available to it. Not a violent death, not a heat death in the conventional thermodynamic sense, but a kind of crystallization into the most stable quantum condition possible. A universe that has explored every available state and finally come to rest in the one from which no further transitions are energetically favorable. Quiet, stable, and in its own way, complete. But before any of these physical endings arrives, long before the last star goes dark or the last black hole fades, there is another kind of ending that may matter more to the only things we know of that care about endings at all. For conscious beings, the loss of novelty may be the real horizon. Think about what makes experience rich. What makes a mind engaged, a life felt to be meaningful, a civilization creative and expansive. It is not simply the presence of matter and energy. It is the presence of difference, gradients, surprises, new configurations, problems not yet solved, questions not yet answered, experiences not yet had. Complexity requires contrast. Thought requires something to think about. And the universe, as it ages, gradually exhausts its supply of contrast. Even billions of years before the physical end, the universe will have become a quieter place. Fewer new stars forming. Fewer new chemical elements being synthesized. Fewer new structures emerging from the interaction of matter and energy. The cosmos will still exist, in the physical sense. But its capacity to generate the genuinely new, the unexpected, the complex, the interesting, will be in long decline. For any conscious beings persisting into those eras, the real ending may not be the moment the last particle decays. It may be the moment when the universe runs out of things to surprise them with. When every question that can be asked has been asked, and every experience that can be had has been had, and what remains is only repetition, indefinitely extended. That is a different kind of ending, not physical but experiential. And in some ways it is the more intimate one. The universe does not need to be empty to feel empty. There is also a subtler problem that runs through all of cosmology's attempts to calculate what kinds of endings are likely, a problem that does not have a clean solution, and that affects how seriously we should hold any particular prediction about the ultimate fate of the cosmos. It is called the measure problem. In a universe, or multiverse, that may be infinite in extent or infinite in duration, probability becomes deeply ambiguous. How do you calculate the likelihood of one outcome versus another when both might occur infinitely many times? How do you count? What unit of comparison do you use? Depending on how you define the measure, the method of counting outcomes, the same underlying physics can yield radically different predictions about what endings are probable. A choice that seems technically reasonable can shift the apparent likelihood of heat death versus big crunch versus vacuum decay by enormous factors. The measure problem is not a minor technical detail. It is a fundamental ambiguity that sits at the heart of any probabilistic claim about the fate of the universe. It means that when physicists say one scenario is more likely than another, that statement is always, implicitly, conditioned on a choice of measure that cannot yet be derived from first principles. The probabilities we assign to cosmic fates are not as clean or as objective as they might appear. And then there is the possibility that the entire story changes. Supersymmetry, if it exists, would introduce a symmetry between the particles of matter and the particles that carry forces, potentially stabilizing the Higgs field and eliminating the vacuum metastability problem entirely. String theory, if it correctly describes the fundamental nature of reality, could introduce new fields, new mechanisms, new constraints on how the universe can evolve. Modified theories of gravity could alter the dynamics of cosmic expansion in ways that change the projected timeline dramatically. Any one of these theoretical developments, if confirmed by experiment, could rewrite the ending we think we are headed for. We are not at the end of physics. We may not even be near the middle of it. The history of science is full of moments when a new discovery did not just add a detail to the existing picture, but reorganized the entire frame. Quantum mechanics did that. General relativity did that. The discovery of dark energy did that. There is no reason to assume it will not happen again. And each time it does, the story of the universe's future shifts with it. The true fate of the universe remains, honestly and genuinely, unknown. Not unknown in the way that a solved puzzle with missing pieces is unknown, where we have the picture and just need to fill in the gaps. Unknown in a deeper sense. Unknown because the question touches physics we do not yet have, observations we cannot yet make, theoretical frameworks that have not yet been built. The end of the universe is one of the largest open questions in all of science, and it sits at the intersection of every other large open question: the nature of dark energy, the behavior of quantum gravity, the stability of the vacuum, the structure of space-time, the origin of the initial conditions that set everything in motion. Every new telescope, every new particle accelerator, every new theoretical breakthrough brings us closer to an answer, or reveals that the answer is more complex than we thought, which is itself a kind of progress. The story of the universe's ending is still being written, by physicists and cosmologists and mathematicians working at the very edge of what human understanding has so far reached. And perhaps that is the most honest and most beautiful place to leave it. Not with a definitive answer, but with the full weight of the question. A universe that is 13.8 billion years old, still expanding, still full of stars, still producing new complexity and new questions, looked at by a species young enough to still be surprised by what it finds. We do not know how the universe ends, but we know enough to ask the question with real precision, real depth, and real wonder. And in the long history of everything, that might be one of the most remarkable things that has ever happened. A universe that learned to ask about itself.